So I think we better get started, just in terms of what we're doing. So this is going to be a somewhat rambling that's a good introduction, but I hope rambling in a good way. Sharing some insights from post-combustion capture, really partly as an example of something going on, but sorry, somebody's talking.
I've muted them, it's all good.
Okay, all right, thanks. Partly with some technical examples, but a lot more, I think, as just an example of a technology that's reached a certain stage on carbon capture and storage, an advanced stage that I hope other technologies will reach soon. So I can get some practical examples of things that have happened, good things and some rather less good things, and think about how that would apply to CCS in general. So, go on. So, post-combustion capture and quite a lot of other things in CCS are now going through these things, technology readiness levels, which was something that was introduced by NASA for particular projects, really, not a general sort of industry level, but nonetheless it's used an awful lot by research councils. Where the idea being that you take a particular idea through all of these stages until you launch it, test, launch, and operation, and then you kind of stop doing research. And other people have come up with the idea that actually this is only the start, and if you're taking something to market, you've got to go through a number of commercial readiness stages until you finally get it up to a bankable asset class. They're just routine technology. And these take on, at least after some examples of the technology, you've reached TRL 9 and go up through various stages of increasing levels and scales of commercial deployment. Where we're at now, certainly with post-combustion capture technology, is that this commercial readiness index is what is being increased, not TRL for the whole technology. Although what you actually do is arguably increase TRL on a lot of subcomponents and sort of subparts of the project. And what I'll be talking about is that open access is particularly helpful for this, for two-way information flow between deployment projects, and it seems especially reasonable when they're government-funded deployment projects, and also research and innovation activities, which are mostly government-funded. And this is, as I say, that it's surprising, but although a lot of technologies have reached high TRLs and still have research on them, I still keep on hearing about CCS research, certainly at academic levels, stops at TRL 3 or something like that, which is just, it's not right, it's not correct, and it's not helpful. Another way of looking at the importance of knowledge exchange, this is something that came out in 2006, has appeared in a number of research council publications, looking at the concept of a funnel for technology development. You start out with a lot of ideas, do basic R&D, then you demonstrate them, and number 4 by the wayside, and finally you end up deploying. And in this model, you get feed forward of knowledge to all stages and feedback of R&D needs in a simplistic concern. I think the only thing I'd say about this is that product considered commercially proven with hundreds of megawatts equivalent deployed, well, that's about one post-combustion capture project. So I don't think that's a sufficient scale. You've got to put that up by a factor of 10 or 100 before it gets completely at the fully mature state. Something else that sets the scale, I think, more accurately was something that was originally developed by Richard Lester at MIT for nuclear, looking at the scale. And they're talking about creating options scale, which is what we're doing in the labs, $100,000 sort of scale. Viability, large pilot plants, single first market examples, multiple examples, tens of billions, and finally, really large scale, up to hundreds of billions, which is certainly the scale for global CCS deployment. But all the time you're getting improvements of different types, and particularly at the larger scale, a lot of learning by doing, learning by using, scale economies, and then continued cost reductions. And then something I like particularly in this model of thinking about it, showing the exchanges. Now we're looking at much more complex range of exchanges, so this is still arguably that funnel, but then bringing in that you need a lot of disciplines. So there'll be a lot of people in these areas who have the specialized knowledge that we would need to develop all aspects of carbon capture and storage, not just the capture plants, but everything. It's all requires knowledge of different types. And these will be people who don't have a clue, initially anyway, that what they're doing will be useful for carbon capture and storage. And equally, we, working in the field of carbon capture and storage, don't have a clue of the detailed specializations in these areas that will be useful. So it's really important to start pulling that together, but you can only, by and large, understand the need for a lot of these technologies if you actually know what's going on here. You don't even know that those areas exist when you're down here. Mobile phones are used as an example for innovation. I can remember seeing people putting forward a very similar figure to this in some of the publications on Peterhead. And as Jeremy Carey, the chair of the UKCCSRC board, points out, the clock rate for evolution in mobile phones is much faster than for different CCS technologies. Clock rate could be analogous also to how fast different organisms can mutate in response to Darwinian pressure. So, for example, mice go through a generation every couple of years, and elephants take hundreds of years. So you can see the difference, and that is a difference between mobile phones and post-combustion capture. Post-combustion capture was certainly talked about in the early 1980s, but it's not gone through as many generations as this. But one thing to recognize is that even with a throwaway commodity like mobile phones, it's not just new ideas. A lot of it is updates, even updates in service, while the unit's being used via software and add-ons. Fundamental research certainly didn't stop when they reached TRL 9. We've seen research in a wide range of components. And actually, despite things arguably ending up in a transformational result on mobile phones, it looks pretty incremental. Perhaps smartphones, touchscreens have been the main new jump, but really you see a lot of similarities between all of the elements. At least you can recognize one stage every time as being related to the previous stage. And then one thing that I thought, well, these aren't exactly open access projects. Manufacturers weren't describing necessarily what they'd done in great detail, but there was very good communication between technology developers, because the products are available on the open market, and people would buy them and no doubt disassemble them in great detail and really quite understand what was going on. So there has been extremely good communication in this market. Really very, very good, governed by intellectual property rights as well, of course, but nonetheless, a really, really rapid communication. I think that, just as much as the relatively short life cycle, the relatively low cost of being able to throw them away, has actually done an awful lot for bringing on mobile phone technology. Going now back to carbon capture and storage, and in particular post-combustion capture, which I'm using as an example because it's already at this advanced stage. This is Boundary Dam, the first operational plant in the world. This is me happily looking at it during construction. And Boundary Dam was approved in April 2011. It was the first CCS power project in the world. It cost about $1.4 billion. There's a slight overrun, but by modern standards, quite low. They refurbished an existing power plant. It captures of the order of 1 million tons of CO2 a year, although actually it's not managed quite to do that on average. It was partly funded by enhanced oil recovery opportunities in Saskatchewan. It opened in October 2014. It was a great day. It used CanSolve post-combustion capture technology. CanSolve, by the time the plant was built, was a Shell subsidiary, and then they upgraded the boiler and had a lot of new bits and pieces. Now, in some ways, we don't actually know a lot about Boundary Dam, but one of the issues that we do know, and I think one of the reasons we don't know a lot, is because there were some amine management issues. Very, very limited details published. And I think partly there's a sort of an inherent issue that when plants get problems, particularly if they use proprietary technologies, then you don't hear very much about it because obviously there's a degree of dispute about what's going on. And people don't want to tell you what's going on, and they may legally be sort of prevented from telling people what's going on until it's sorted out. But in this case, to look at the scale of the problem, this is a direct quote from a blog by the chair of SAS Power in 2018, March 2018. And he said that they'd forecast a budget of about $5 million a year for solvent replacement. This is, bearing in mind, it's on a capture of the order of 1 million tonnes, so that's $5 a tonne just for the solvent. They'd actually spent 17.3, I think capturing rather less than 1 million tonnes of solvent, so that's $20 a tonne, and that had carried on going at least until 2016. So that was a serious problem, but people didn't get to know very much about it. Fortunately, some pretty dedicated engineers kept the project going and managed to at least get workarounds on these problems. But I'm not aware of any researchers who've actually gone in and tried to understand the fundamental problem and to help with the project. There may have been some, but I don't know who they are. This is just some of the data. This is showing more recent performance. This sort of set of figures gets published every month on the power plant. So far, since they started up over 6 years, they've captured 3.3 million tonnes, so rather less than the average amount, perhaps partly because the demand for CO2 isn't there. You can go and look at these figures. They had a good month last month, 99% variability. Another example, post-combustion capture. This is the second plant that was built. Petronova is a joint venture between NRG, the plant owners, and JX Nippon Oil and Gas Exploration that became operational in 2017. So a little bit later. It was actually originally set up as a project with Fluor. Fluor did some development work with NRG on a very similar concept, but then it was taken over with MHI technology. And some of the key things to note: fairly typical sort of connection to the stack, a long piece of ductwork connecting the stack with the capture unit. It looks small, but it's the sort of thing you could drive a car through. And then you've got the capture facility, in this case, pretty tall. The stripper where the CO2 is released. And then this plant uses a separate gas turbine unit, which they bought secondhand, I believe, to provide the steam and power to drive it. This is just another picture in more detail of the unit, showing some of the bits and pieces. And one of the interesting things here, I don't know whether they picked up the issues at Boundary Dam, but they put in a washing section, a wet flue gas cooling and washing section, rather than a dry cooler as at Boundary Dam 3, to wash out as much of the fly ash and other objectionable materials as possible before you actually got into the absorber. This plant also had a conventional flue gas desulfurization stager, which helps to wash out a lot of the impurities. Now, one of the interesting things, and one of the lessons to bring up, was that MHI said, and this is a paper published in 2010, that before you actually go and do a commercial project, you need to test for a long time and verify the influence of, and very importantly, develop countermeasures for related impurities containing coal flue gas. So this is really quite important stuff. And you need to worry about the buildup of dust. So this is practical example of where they got to with some real experience. And this is how they did it. This is a very, very large pilot unit, 500 tonnes a day, 150,000 tonnes per year, that was developed on a plant close to Petronova and run for 2011 to 2015. So just looking at what was going on at this period, we had E.ON possibly looking at deployment in Europe with an MHI plant. You had Southern doing this plant Barry. Cansolv, I think, looked at doing a deployment with E.ON, I think in Germany. They certainly built a unit at Aberthaw in Wales, but I don't think that was run very much because by that time it was obvious that the plant wasn't commercially viable. Subsequently, Mitsubishi Hitachi, as they are now, which isn't the same as the original MHI Solvent, did some work at Shand, and also Cansolv, probably in connection with some of the issues they'd had, also did an extended period testing at Boundary Dam, at Shand. Now, there's a lot coming on at the moment, and people are obviously picking up on this sort of need for work, extended work on solvents, and you could, by analogy, pick other problems and other technologies. And this is a paper that's just come out, 2020, just came out a few weeks ago, looking at results from an RWE pilot plant in Germany. And this project ran, remember we were talking about thousands of hours, this project ran for nearly 2 years. And one of the things they saw was using MEA. In this plant, they got an exceptionally long time, 5,000 hours roughly, before anything very serious happened. But then eventually exponential feedback took place. They got rapid degradation, several bursts of it, and they eventually, at least for a period, managed to do some solvent cleaning using ion exchange resin and keep the concentrations down. But I have to say, this wasn't a commercial test in many ways because they didn't start out with the reclaiming, which probably would have been useful, and they didn't run it for long enough to demonstrate reclaiming. But it's obviously a very interesting step, and this is in fact about the only example I know where you can actually see this type of test and some of the things that actually happen in real life in the public domain. Oops, wrong way. Interestingly, yesterday, MHI announced they were going to do a similar test at Drax in support of the feed study they're looking at there. And they're going to do a 12-month pilot. They're going to test 2 solvents, KS2 and I think it's KS3, another solvent. KS2 is their standard one. Scale is quite small though, 300 kilograms a day. That'll be something like I don't know, maybe a 20 centimeter diameter absorber, which is very small. But nonetheless, a long time. So it shows that, you know, what people need to do, particularly for large scale activities. So just an example of what you need to do on these mature technologies. You need to go for long running hours. We've seen 13,000 hours, 5,000 hours plus, 7,000, 8,000. Problems actually, I think, when programs were curtailed. You will need to do at least 4,000, 6,000 hours of testing. We've seen our RWE running for over a year, but all of these tests, despite the really quite considerable cost of them and the length of time they take, don't give you a fraction of the data that you would get from actual operating power plants, because those will raise questions that you don't even see on a pilot plant. You know, there's many more things going on in a real operating power plant. Generally, they're more complex pieces of equipment. Real power plants often take a range of fuels. there's a lot more data to be gained. And I think it's very interesting to reflect that we're really only scratching the surface of what we can learn, and the examples we can see of fundamental processes going on that we perhaps didn't even realize would happen with the current pilot plants. And we really do need to get some information from actual operation to take things forward. Now, I'm going to show here a cautionary tale, which also applies to large-scale CCS deployment, but it's fortunately not post-combustion capture. So this was an article from 2014 about a CCS project in Kemper County, Mississippi, where they have a lot of lignite available, and they wanted to carry on using that lignite without emitting CO2. And the Southern Company was looking to build an entrain flow gasifier, produce essentially hydrogen with some carbon monoxide in it a little bit, and then burn it in a gas turbine and generate power. And the project was originally estimated to cost a couple of million, and at this point, oh sorry, $2.8 billion, a bit more. And at this point, the overall cost of the plant had reached more than double that. So there was some debate about whether it would happen. But by 2017, it had stopped. And Southern had abandoned trying to run the gasifier. They just ran the gas turbines that were supposed to burn hydrogen on natural gas. And this was another report that said there were complex technology was one of the factors. Then there were unknown startup operation and technology risks. So I think that goes back to the example of needing to do these very long-term trials, and also where it's available, get knowledge from other people doing actual projects. And then something that was not related to the technology was that they were looking to make a gas to burn in a gas turbine, essentially to substitute for natural gas because they had cheap coal. But when fracking came along, the project had cheap natural gas. And then, as I say here, the cost by this stage was expected to have tripled. Although interestingly, and I don't know if this is a good ending or not, again, very, very recently, Southern announced that they were going to look at putting post-combustion capture on the gas turbines. So they've got another capture project. They've changed the name Kemper and called it Plant Ratcliffe. They're looking at using storage, which is right under the site. I mean, this is, if you're in the UK, I think the idea of being able to just drill down a kilometre or two under your site and get good storage with a halite layer, very good sealing halite layer above it, seems unbelievably good. But anyway, they're able to do that, and they're looking at retrofitting it. But they have this legacy of an enormous project overrun, quoted here at now 7.5 billion. Now that legacy to overcome, both externally and internally. But as I say, they're looking at post-combustion capture on that plant and some of their coal plants too. So it's a bit of a cautionary tale, but maybe with a happy outcome in the long run. The total cost, though, is important, and this is now an example, again, very, very topical. It's interesting that a lot of things happening. Looking at the Northern Lights project in Norway, and this does relate to post-combustion capture, and it also gets onto this idea of learning. So you can see we're sort of going around the same issues. And Norway, this is translated from the Norwegian actually by Google, so this is not quite what you'd expect. Any inconsistencies are just because of that translation. So Norcem Cement Company are planning to capture about 0.4 million tonnes of CO2 per year, and also an incinerator in Oslo was looking to capture about the same amount at Clementsrud. As we then know, it will be shipped around to the west coast of Norway, put into a pipeline there and stored in an aquifer. Now, the original costs were expected to be somewhere between 13 and 17 billion, with operating costs between 6 and 8 billion. And this report, which is in Norwegian, by the way, said an expected total cost now of 25 billion kroner, about 2.6 billion for building and 10 years of operation. And interestingly, the state takes 80% of the bill. They said it needs about 10 times current carbon prices, which is very interesting. So I guess that's at least $200 per tonne or 200 euros per tonne. And then interestingly, because of these costs, they said it may be better to have one capture project instead of two, because that leaves more space for imported CO2, other capture projects. These are other capture projects outside Norway. And because it reduces the cost without necessarily reducing the learning effects. And Norcem appears to be a better deal. That's really quite interesting. I have actually been to Norway talking about open access to increase the learning. I don't know if they're thinking of doing that. I rather think not, but it does emphasize the importance of learning from these early projects, and also how sensitive you are to the total cost. And I don't know if they've said it in the report because it's in Norwegian, but if you're worried about the total cost based on the initial estimates, then you must be really worried about cost overruns. And this is something that needs looking at quite a lot, and to the extent that you can reduce cost overruns by getting better information exchange, or at least when you get a cost overrun, treat it as a learning exercise instead of just something that turns into an argument and a matter for lawyers, then it's really quite good. So staying in Norway and now going back to open access, just to give some examples, this was the previous attempt by Norway to go for large-scale deployment with post-combustion capture at Kørstad on an existing, now scrapped, gas-fired power plant. This shows the capture unit, a couple of absorbers, and the stripper. This is the stack of the power plant. The power plant's over here, not shown. And a feed study was done using 35% by weight MEA, non-proprietary solvent. After 10 years, the results became available, and they're now on our website, thanks to cooperation from Bechtel and Gas Nova. And it's the feed report plus over 200 supporting documents. It's really quite detailed if you want to get a snapshot. I have to say the technology has not changed an awful lot since then, because plants haven't been built. And also this plant is, the sort of feed study has been used as the basis now for a DOE funded feed study in Texas by Bechtel on another gas plant there. This is just showing where the plant was, quite close to storage regions, which was handy. This is the power plant. This is where the capture plant was going to be. And this is looking at the unit, and you can see you've got this, just some of the issues that are common. You've got this long connecting duct because the plant wasn't designed to have CO2 capture. This is the stack of the power plant. Again, a duct you could drive a car through, going off. And this shows the actual connections. Basically just essentially cut a lot of holes in the back of the stack and get the flow through. And interestingly, these issues of connection become very important for running post-combustion capture units, one of the main sort of issues. So it's interesting that when we're doing research, we think about, in some ways, more sophisticated issues, but basic issues like that come in. And then they introduce a lot of other potential for operational changes, because one of the obvious things here is you don't have necessarily anything that diverts the flue gas through these holes. You have an open connection to atmosphere, and you just determine the flow through here by the fan that's sucking the CO2 through. And that raises interesting issues because of the potential for dilution, but it also means that you've got a very flexible system. So you can, it sort of automatically adjusts. You know, you don't have to try and keep the exact flow going through the capture plant so that the power plant doesn't sort of choke itself and stop. There's some very interesting characteristics there. Also, one of the things that came up in this plant, which is now ubiquitous actually, is this second point here, the use of stainless steel materials of construction. So we have spent a lot of time, I think, wondering about corrosion in power plants and the use of low-grade steels, but I don't think that's going to happen in practice. So that then gives you a lot more choice in the range of solvents you can use. And this point is made that you will be able to upgrade the solvent later and have a fair choice, because you can take, you've got a fair amount of corrosion resistance, not unlimited, but a fair amount of corrosion resistance in the basic technology. And then some other points that were made about going down this open access route is that because you weren't constrained to particular suppliers, you could buy cheap solvent and also go to competitive bidding on the hardware. One of the things that was important, and something that hasn't come up in a lot of sort of academic studies on things, is solvent management. So we're not just concerned about the energy. In fact, that's a secondary consideration, as we'll see, particularly on natural gas. But bearing in mind what happened at Boundary Dam, we're very concerned that the solvent stays in good condition. And one way to do that is to continually distill effectively the solvent to take out the good stuff and reject the bad stuff that's accumulated. And you do that in a thermal reclaimer, a still, and you feed the good stuff back into the circuit, into the stripper, and you get rid of the waste for disposal. So that's something that's very important to look at. Because it's part of the system, it doesn't take a lot of energy, but it does need looking at. And there's a whole set of reactions in here which nobody understands, which are absolutely crucial for improving successful operation. One other thing, practical problem you get, is that on this unit, they needed to supply steam for other purposes, and they might not have been able to get enough steam. So they looked at, in this case, using an auxiliary boiler, but you can't do that in a lot of applications because you're concerned about the CO2 from the auxiliary boiler. So one of the things we've been looking at, which again is not standard, but you sort of come at when you're doing open access, is looking at alternative ways of providing the heat, which then raise other opportunities. And this is actually another open access post-combustion capture study. In this case, it's a pre-feasibility study, not a feed study. And this was using even more concentrated MEA. And partly that was done because it was open access, but also it was on a brown coal plant, which didn't have flue gas desulfurization. It had very low sulfur, not zero though. And it was obvious that you were going to get significant reactions between sulfur and the solvent. And you'd have to be able to overcome them basically by cleaning up the solvent, and you would take some losses in that. Therefore, you needed a cheap solvent. So on this project, there's a number of similar sort of concepts on the plant, certainly the continuous reclaiming. This is just showing where it is. This is the power plant. The road doesn't go right through the middle of it. It turns just before, but it looks like it does. And also this power plant, partly on the road, you have to watch out for the kangaroos because the kangaroos like going around the power plant. It seems a protected site for them. Right in the southern tip of Australia, Victoria. There's a lot of good CO2 storage out here, which Australia is looking at developing at the moment, which is why the plant was topical. Now, we were just talking about steam extraction. This is showing the point on the steam turbine where conventionally people expect to be able to get steam. And this is the crossover between the intermediate pressure turbine and the low pressure turbine. The low pressure turbine is here. And these are the two crossover pipes, and they're pretty difficult to get access to. There's two of them, well, four of them, sorry, there's similar ones on each side. And they're quite difficult to access. So in fact, what we did, and this is now looking at a model of the unit, because you can see it, these are the crossover pipes. And these are the pipes that are used to bypass steam around the steam turbine where the plant's starting up. They have very long startups on these plants because they're burning a fuel which is 60% water, and it takes a long time to get it burning. And while they're doing that, before the steam reaches a suitable condition to go into the turbine, they pass it around and dump it into the condenser, which is under here. And because these pipes were there and because they were easy to access, this is the outside of the building, we actually decided to go in and take the steam away from there. So we didn't use the conventional extraction. We took high pressure steam, let it down through a turbine, desuperheated it, and then put it in the reboiler. Now, that costs you a bit, but it gives you a great deal of flexibility, and it allows you to have quite high temperatures here if you want. And we're looking at the potential for doing similar things now on combined cycle plants, because it may also be difficult to extract steam from the main body there. And there's a whole range of slight problems with temperature, but also now you've got a lot of things you can imagine doing because you've got this high temperature steam available, potentially, and it allows you to contemplate pushing up temperatures in the capture plant in a way that you wouldn't be able to do, running reclaiming, possibly doing enhanced thermodynamic optimization. A lot of interesting potential, but you only start to see this thing when you look at real projects and people tell you what they're looking at, and you get these ideas. This is just looking at the power plant, very large absorbers, very short of space. The retrofits we looked at with long ductwork basically got over the problem of space by moving off somewhere away from the main part of the plant and building an absorber which really didn't capture all of the CO2 from the site. If you want to capture all of the CO2 from the site, then you can't necessarily find a lot of extra space around it where you can put these plants. This is showing one unit. This is showing, if I jump on a bit, this is showing how you put these units around the plant, and it's very, very tight. Each of these had 2 units in, and these are the capture plants for those units. So again, this raises another set of real-world issues which translate into fundamental research issues of how do you compress processes. And then, because you can't have a very easy flue gas ducting, you want to vent CO2 from the top of the stack. That's a treat a flue gas vent at the top of the absorbers. And then you get another set of issues to do with how you balance the energy, how you balance the water, and then particularly how you manage emissions to atmosphere. A lot of interesting issues, and again, problems which you may not come to directly in the same way if you're looking at even large-scale pilot projects. Something else, again, topical, which I won't say too much about, it's ongoing work looking at flexibility, but it actually started a long time ago, 2004. We were looking at this, Hannah Chalmers in particular carried on a lot of work on this, looking at solvent storage. And solvent storage can do a lot for you in terms of flexibility, because at the moment in a conventional system, you're circulating solvent around. So you take in solvent lean, it can absorb CO2, you trickle it down through a packed bed, it absorbs CO2 from the upcoming flue gas, comes out the bottom rich in CO2, you do a cross-flow heat exchange with hot solvent, you warm it up, and then put it in a stripper where essentially it's boil off the CO2, collect that up here, take out the water. You put heat in with the steam, with condensing steam to boil off the CO2. Then you take the CO2 back and send it back to the absorber. Now, if you run that system close coupled, obviously the performance of one bit depends on the performance of another, and you can't disaggregate them to control it. But if you then got some buffering in terms of the rich solvent and the lean solvent, then you can decouple these two elements and get a very nice, flexibility, either for rapid response, for startup, or even for effectively providing electricity storage by storing solvent when electricity is cheap and using the stored solvent to run the plant when the electricity is expensive and getting a higher output. So there's a lot of games you can play. But again, when you look at this on real plant with real problems, you get a whole set of issues for fundamental research and learning. Quite a lot to do with actually what happens with the solvent while you're storing it. Does it degrade more because of that? And even simple things like, well, if I'm going to do this, the physical, the cost of that amount of solvent starts to become significant. And I now have a different optimization in my solvent properties with just the straight cost of a tank full of solvent becoming potentially quite significant. So a lot of interesting things come in with real world issues. So just finishing, why is CCUS different? We've got an example with post-combustion capture, but as I say, you could say this, I think, about a number of other technologies that are coming up to deployment. There'll only be a few big post-combustion capture projects globally over the next decade. And I said 5 to 10, and I think that example from Norway, where they might go down from 2 to 1, is a pretty good example. In the UK, I don't know how many we'll get, but it's single digits. And then, if we're going to tackle climate change, we won't need a huge increase in deployment going up to hundreds, mainly via retrofits, I think, to meet climate targets. And the problem is, unlike mobile phones, there's no automatic access to information. You can't buy one and have a look at it. And I have to say, it's customary for reports on these things, and most of the projects are supposed to report what goes on, but they're all allowed to redact information. And without exception, apart from the open access projects, all the really useful information is redacted. It's not there. It's taken out. They say that's proprietary. We can't tell you. It's quite interesting. So, there's a lot of writing, but when you actually want to look up important things, there's very, very little real information there. So if you want to get good information exchange, you need to have some level of openness, particularly for government-funded projects, where they're open technology, which means you can test multiple solvents, and you need to use a non-proprietary generic solvent, at least for an initial period. If you do that, then you can have good knowledge exchange internationally, which is important because no one country can do it all. And you can also get good commercial competition to reduce costs because it's open, people see what people are charging for the basic hardware. Bearing in mind when we saw the Norwegian example, costs are really important, particularly for these early projects. Then that's a good way to get better value for government expenditure on deployment and R&D. And very importantly for the world, it will increase the rate at which PCC technologies will improve. And as I say, you can say the same thing, I think, about all other aspects of CCUS and other technologies. So you can deploy multiple innovations, including through in-service upgrading. On solvents, a classic example is you can try out multiple solvents without building a new plant, costing of the order of €1 billion or something for every one. And then you can get information exchange in both directions. But you can, as well as solvents, we've sort of concentrated on solvents. People tend to fix on a few aspects of a technology, but there's actually many, many different aspects. And I'll remind us again, but remember all the different dimensions and specialized technologies in which you can improve performance. And the question is this going to cost money? Well, it's very, very hard to get good costs for different post-combustion capture technologies, and I think even harder for other technologies. But there was a study done for the World Bank trying to answer the question, what's the best post-combustion capture technology to buy? They did a study with a number of commercial technologies, and they compared it with 30% MEA, which is generation 1, open access solvent. And for a natural gas combined cycle, and I think there's some reasons why the flue gas you're capturing from is important, but for a natural gas combined cycle, really very, very little difference in overall cost of the odotes would just about be lost in the noise. It's sort of 37.6 dollars per ton versus 35. And with a second generation open access solvent like 35 to 40% MEA, or a solvent called Caesar 1, which was developed on a European project of that name, which is piperazine and AMP, I think you get very similar performance. This is just showing the detailed technologies and giving some references. So just to finish, we've been running a number of open access workshops with people who are working on the particular area. This was an international retrofit workshop with people from a number of countries. And we've had other workshops and webinars since then discussing particularly this overlap between deployment and research. It's very, very interesting. And people exchanging information on deployment. And then just to remind us that where we're at, and this is really important, I think, both governments considering funding deployment and also organisations funding innovation need to recognise that the game has changed from doing research to increase the technology readiness level to doing research and deployment to actually get this stuff from the first projects as rapidly as possible up to a bankable asset class, something you can build out rapidly, excuse me, in the hundreds. And a good way to do that is two-way information flow. And we just won't see that if people have to protect proprietary information when they do a project. Reminding people about this, looking at the model where you've got different stages, talking about now in the tens of billions up to billions of dollars of cost. And finally, a reminder that actually CCS involves lots of technologies which aren't classic CCS. And I think, as I say, I said it before, but I'll say it again. We will realise a transition from, in the UK, from a phase which is I guess I call pre-deployment to post-deployment, when we successfully go from working essentially as a CCS community to being a whole research community and reaching out to all of these areas where they've got necessary specializations but don't yet know that they can use them in CCS. And we somehow need to manage that interaction, but we can only manage that when we actually get real information out of these projects. Because a lot of these things you can't understand and develop a need for how they're used until you see really complex projects that actually get the full range of issues exposed. So this isn't to look at, these are my references, they're on the, they'll be in the presentation when they're out. But you can get information on large scale projects, but ultimately this will be work in progress. We've got the prospect of seeing a lot of projects being deployed. And I'm really looking forward to getting information out of those and seeing how we make inputs ourselves, and also, as I say, very importantly, with colleagues who we haven't really identified yet, to get the very best out of these projects and get the cost down so that people are prepared to build them in the hundreds that we need to actually make an impact on climate change. Okay. I think questions.
Right, thanks, John. That was very interesting. When you were talking, sorry, it's Louise here from Swansea University. When the end section of your talk, made me start thinking about like big research facilities like Diamond Light Source, where people from all different disciplines turn up to do all different types of experiments. Do you think it would be feasible to do something similar, like make a large-scale CCS facility, or carbon capture at least facility, not necessarily storage, of course, and kind of like what PACT do in Sheffield, but at a large scale. So as you said, new solvents could be tested at like a working large scale before being used in other carbon capture plants.
Mm-hmm.
So that in effect, people wouldn't have to kind of commit to the technology at their own carbon capture setup. I mean, do you think that's a feasible way to go forward? Like,
yes, I suspect there may be something like that certainly happening. Yeah, I think that's distinctly possible that people will do that at the larger scale. And in fact, what they'll do, I mean, if you think about it, if you did go down the open technology route, you've built in some ideas for using different solvents. And the risk of using a new solvent when you've already got an operating plant and something that works, provided you can test it in the sort of pilot unit that you're suggesting, is very low, because what's the worst that can happen? You have to clean up the plant and put your old solvent back in and carry on.
Mm.
Whereas if you're building a new plant with an unproven solvent, the worst that can happen is, you know, the project fails, costs overrun, you get into litigation. It can be pretty bad. So it's a really interesting way, yes, to not only get the first one, but to get subsequent ones. And I really hope that if we were doing that, you'd effectively, on post-combustion capture, get over this problem of having a relatively slow clock rate by, at least for a period, changing solvents every couple of years, assuming you can come up with improvements.
Yeah, it could lower the risk to projects individually, and
oh, yes,
possibly create a kind of large-scale research community and generate more idea sharing if it was like that.
That's right.
I mean, PACT in Sheffield, is that, excuse my ignorance, is it fairly unique, or are there many countries have kind of pilot scale testing facilities?
Yeah, most countries have pilot scale. Well, a number of countries. The ones who are CCS active.
The leaders, I guess. Okay.
We're one of the smaller ones. There's something called the International Test Centre Network, ITCN. PACT is leading that. It's a very formal organisation. We're running it for a couple of years. Somebody else will be taking over soon. And that links between these pilot test units. What we haven't seen, I don't think, and there's been some talk about doing it, what we haven't seen is a very good interaction between projects. And I think partly because the projects aren't there, and the ones that are there are quite quiet. You know, they're pretty much locked down for information. But if we were able to get some open access large scale projects, then you could also have that dialogue, which would be very valuable. And as I say, you need to think about that for other technologies as well. This is post-combustion capture, but you could look for things on storage, you know, any aspect you like. I think post-combustion capture is more secretive than most. I think storage people tend to talk a bit more because they're dealing with geology, which isn't proprietary.
Okay. And I guess it's secretive within the stakeholders, like the companies themselves, rather than secretive within countries, depending on who pays for the bulk of the project.
It's proprietary. I mean, you're talking about internationals who are often developing technologies in countries which in some ways aren't their own country, but I mean, they're multinational companies, so what I can say. I mean, Patrick raised the issue. And then Patrick, do you think technology owners are scared of sharing that? Oh, do you want to ask the question, Patrick? Can you come on rather than me?
Sure, John. Can you hear me?
Yeah.
Lovely. So let's put it that way. What I'm doing in my PhD is comparing apples and oranges all the time. I'm trying to compare different solvents. And you nailed it earlier when you said what we want to answer is what is the best technology? And I'm afraid we can't put a number answer to that. So the problem that I see is if you own a technology, you don't want to give your data away because that would offer your competitors an easy chance to prove that their technology is slightly better. And let's say the certainty behind, for example, the World Bank cost estimation, I mean, there's a reason we haven't seen error bars around those cost numbers. So what do technology owners gain by sharing such information other than risking losing, let's say, projects and income?
They gain absolutely nothing. And I'm not saying that you should share proprietary technology information. I think it's unreasonable to ask people to disclose proprietary information. So that's why you would go, you'd look to do an open technology plant. You'd run it initially and probably procure it contractually using a generic solvent. That way you can go to multiple suppliers. And then you, having tested other solvents, will put other solvents in there. And you may or may not tell people how they perform, but probably what you end up using will tell people what works best. But you don't tell people, you don't try and get people to disclose proprietary technologies because they won't, not willingly. It's interesting, I think, thinking about this thing about mobile phones is clearly that's proprietary technology. It's protected by patent to the extent it can be. But notwithstanding that, you still do get free communication. So, you've raised a question about, is it proprietary, how well it works? And that's, yeah, I mean, it is, it's useful, but it's a real pity that users can't be sure how well things work, which they can be with mobile phones, when the patented position is really protecting how you do it, not so much the result. And so I think we're just in an interesting situation where, what you can and what you try to keep secret is different for different things. And it does seem that you absolutely no interest in finding out how people do things, or at least not trying to breach their basic IP rights. That's not helpful. But we're clearly not making progress when you've got a number of alternative ways of doing things, and it's not very easy for anybody to work out how well the relative things work. I mean, it's not economically efficient. Do you want to add anything to that, Patrick?
If I might, before we shift to Jennifer's question. So I think it's very interesting you brought up the telephones and mobile phones. And I think there are only a handful of providers back then. And I think for CO2 capture, solvent-based CO2 capture, we have maybe less than 20 companies or technology providers in the world that could pull it off in scale. And then I thought about what Tesla did with their patents. They open up their patents so anybody can use the technology, because I can only quote the news on Elon Musk saying he wants to drive the shift towards electric mobility. And then I've come only about, I think, one technology, that's the Pacific National Lab in the US. They open up the patents for free of their water-lean solvents. So if one company wants to use them, they could use them for free. So maybe that's something interesting that's going towards this open source sharing of information, and then not having to fear that someone is stealing or copying your IP.
Yeah. Well, I mean, there is an idea, and I'm not entirely sure I'm speaking correctly here, but I think there's an idea that anybody can use patented information, at least in principle, if they make a reasonable payment. And that, you see that going on actually in companies suing for awards. So you know, arguably that is the correct way to do it, that people, first of all, know that something's worth using. If it is worth using, then it's worth paying to use it, and then you can do it. But we're not at that stage yet. And I think if we have a combination of open access using generic solvents where you really can see everything that's going on and get a good description, even within that, you'll have patented bits like, well, you know, all of the hardware, really, pumps and things like that often contain proprietary information, instrumentation, but you'll have general understanding of what's going on, and you can do things. And then you have a hybrid system where, yeah, if someone can come up and say, look, this solvent is genuinely better, I've patented it, it's mine, you've got to pay me rights to use it. People can say, yeah, okay, you know, we'll make a decision on that, we'll pay you what it's worth, and the market will decide. But at the moment, we're just not there. And as I say, I do think it's interesting to look at this feature of these, you know, these large plants, very small numbers, very difficult to access. You can't buy one and try it out. And just to compare that and think how innovation is different in different areas. Yeah, so John, we'll come back to Jennifer. John, do you want to make your point?
Yeah. This question around patenting and protection and technology worries. With an article like a phone, you can tell if someone's copied, because if they produce the same phone, they've put it out in the public domain, and then you can go to a lawyer and say, please sue them, they've infringed my patent. You can see they've copied my design of this button or this widget, or, you know, this connector or something like that on the phone, which is covered by a patent. With a process, unless you find some way of gaining access to a plant, you don't know what's happening on that 100-acre site. Mm-hmm. And the product, particularly that these processes are producing, is carbon dioxide. So how are you going to tell that that carbon dioxide was processed through your patented product, a process, or through someone else's process? Mm-hmm. So over the years, the process industries, the whole chemical industry, has had this dilemma of, do you patent protect things, or do you try and deal with proprietary knowledge in different ways? And often companies have used trade secrets. There's another reason for that. Patents expire after 20 years. So if you'd come up with a patent in the year 2000 for your latest process, then I'm sorry, but you filed it, but that was 20 years ago. Unless you've got some new way of extending that patent, that's now public knowledge. Mm. Whereas if you keep it as a trade secret, those are pretty much indefinite, as long as you can prove that you've only disclosed to people under a non-disclosure agreement.
Yes.
So you've got this situation where it is a little bit against doing patents. Now, where there's a difference is perhaps the solvent, which was the example you gave, John, because that is a product that you can put out. It's more easy to check. And someone can say, well, you'll have 6 gallons of solvent X. It's a product. And you can sell your patented product that way. Whereas the process, that's a little bit more difficult.
Yes. Well, certainly I think the idea would be that you don't ask people to give away any of their secrets.
Yeah.
You just, if they, the only thing that would be useful to know is the ultimate performance. And that's, I don't know quite how sensitive you think that would be, but, at some level, you're happy to say, look, this is a black box, or at least it's using, you've done something with the basic design that's made it better. We only care to know how much better it is. We don't care how you've done it. Do you think that's an issue?
Depends which part of the market you're in. There's a big difference between process operators and which is, I guess, my background in the chemical industry, where you're operating a piece of plant, and someone who's a provider of technology. So you've got the construction companies that will build stuff. You've got design companies that will design and sell proprietary technology. Quite often those work hand in hand, and some of them are part of the same, the bigger organizations will have both. So they'll have some proprietary technology and construction. So it depends which part of the market you're in. So people could have quite different views on that.
So John, if I might quickly say, apologies for my naivety here, but I thought the concept of a patent is you're being, or you're the only one who can exploit what you came up with, and you're being protected for those 20 years by the market. So what is the difference between a trade secret and a patent? Because I appreciate that after 20 years, everybody can use it. And I thought that was the deal that society made with inventors, that inventors get credit for their invention, are able to utilize it for 20 years, and then society is able to utilize that for free.
You give away by publication the knowledge of what you've done, and you can license it, which was the other point that John made. So it doesn't have to stay just with you using it. A lot of people patent technology with the sole purpose of selling licenses. The idea is that their proprietary technology will be used by a lot of other people, but they'll have to pay for it. The trade secret approach is simply that you have to show, if it's ever challenged, that you haven't disclosed it to anyone, and it's what you're doing yourself and has always been proprietary. And certainly the recipes for herbs and spices for a well-known brand of chicken, Coca-Cola is another thing, all those sort of things. The advantage of trade secret is it doesn't die, but you don't tell anyone what it is. It's your secret. And those are the two main ways of dealing with intellectual property. The other thing to bear in mind is with patents, it's by territory. So your patent in the UK generally is covered under an EU, European-wide group of patents. But if you want it worldwide, you'd certainly go and register it in the US. You'd probably want to try and enforce it in China, but that's always difficult. And one or two other jurisdictions. And you always have the choice when you patent is how many thousands of pounds am I going to throw at this, as to how many different patent offices I'm going to file it in. And you can end up with quite a long list, depending upon which jurisdictions, because they only cover certain jurisdictions.
So, where this gets interesting, I think, on these projects, is that a lot of this work has a significant amount of government funding. And as we've seen from that example in Norway, but it's very common, a lot of this funding is given on the understanding that they'll be learning by doing. And so I wonder to what extent we're in a pre-competitive situation where people would think that different conditions applied. I don't know if anybody here is sort of qualified to answer that, but it does feel that the situation is different anyway, just at the moment. Jennifer, you had a question?
Yeah, you're better off reading it out. I've got a bit of a noisy 4-year-old in the background now.
Oh, very good. Okay. Yeah, the four-year-old can't read it for you. Perhaps that might be a way to keep them quiet.
Give him another month of lockdown, and I think he probably could, frighteningly enough.
Okay, we'll take you up on that at one of our next meetings. So Jennifer was saying, plants are in operation, but the pilot testing keeps on going on. When we know technology works, is it really necessary to keep on pilot testing? And then you said, well, maybe I'll do the second one. Drax was already running BEC, so why is it now doing more trials? So Drax was actually running pilot trials of, I think it's sea capture technology and advanced technology at small scale and releasing the CO2. They're not actually doing the full scale stuff. Why is it necessary to keep on doing pilot testing? Well, one of the issues is that there's different aspects to whether or not technology works, and it may work okay at a sort of an immediate level for a number of months, so you get the basic performance. But with post-combustion capture, and I guess with a lot of other things, there's changes going on. You're picking up impurities, or things are wearing, or various things happening over an extended period of time, and you would need to do longer term testing to see that. And then if things are happening that you don't like, or that you think could be made better, then you have to try those out, and you have to try those out for a long time. And there's an almost limitless number of tweaks you could want to do to a technology to improve it. You don't necessarily want to try those out on your big plant, so you'll try them out on the smaller one. So if you want to improve things, having pilot testing that you keep on using all the time is very, very valuable.
Okay, so having the pilot plant in testing phase doesn't necessarily mean that there isn't still carbon capture going on a bigger scale. It's just that the pilot plant is used to refine things.
Exactly.
Got it.
Yeah. And it's just like, basically, you know, it goes back to this commercial readiness, that no technology is mature until it's been through lots and lots, well, you know, sort of never, but it doesn't approach maturity until it's been through lots of cycles. And when you've got a technology that's relatively slow moving, because it's big and it's not built in large numbers, that'll take a long time. So it's just, I mean, it's particularly interesting with post-combustion capture, or sorry, CCS generally, is that I think because of the nature of the market, you get everybody now just saying, oh, this is really expensive technology, we need a higher carbon price. And what they're really saying is, until we get a global push on this and everybody has to do it, it's basically, you know, we're just going ahead and sort of doing it in the hope that everybody else will later want to do it, and we've started something useful. Now that's a good thing to hope for. But you then get the characteristic, we can see it coming, that you've got countries working on this, investing essentially speculatively and hopefully in relatively small numbers. And then all of a sudden, assuming the world decides, yeah, this is a problem, let's do it, and everybody does it, you then get you want to get, and it's justified to get, a very rapid increase. So you don't sort of get this natural market building up that drives itself. You get this I think, a sort of a step change, and then all of a sudden it goes from being something you're doing as a public service to being something you're doing because you've got to, you know, because basically it's a global commitment. And if the major power blocks have decided to do this, USA, China, Europe, have decided that they're going to do this, they'll make damn sure that everybody else does it. So you know, it's this interesting market.
Just to support what John's saying about pilot plants, Jennifer, I used to work in the fibres industry, and we had processes that were 100 years old that people had been buying man-made fibres from for decades, and we still had pilot plants that were run to try out new variations, small changes, to test new ideas, and there were always pilot plants running in the background, even though those processes were by any measure you would say quite mature. So it's not uncommon to keep running pilot processes after the point that you've identified that, yeah, that process will work, but there's always outstanding questions.
Yeah, I understand that now. I think I think because we know that CCS has been so stop, start in the UK, and now it seems to be on another round of getting going again, I thought that it was the case that we were still stuck at kind of pilot phase, and it was like, oh, we'll test, without really a view to then scaling up. It was just, or or they were doing that because it was like, oh, this seems to be on trend and we should show that we're doing it. And this is the kind of the safe way to do it, rather than actually going for it and really doing CCS. I thought it was a bit of a, I was wondering whether it was a cop-out.
I mean, I think, you know, there's some elements of what you're saying has been, but I guess what I'm talking about, and perhaps I'm going on too much about pilots in a sense, although they're part of it, is just this example of post-combustion capture as being something that shows what happens when you take CCS, and you know, you've got to do everything, not just post-combustion capture. But when you take CCS away from this purely pilot stage to deployment, and you've got a lot of opportunities, you've got a lot of potential problems and cost overruns, and a lot of things you can do, and really just thinking how kind of the world of CCS that we're working in changes, and then how that feeds back into the research community. And as I say, there's this thing where you need to get information exchange, and that's a lot of what we're talking about. You need to get supplementary information. And then we do need to really widen the input to the range of problems that are going on, and be much more sophisticated and complex, really, in the way we handle these problems. But it's easier when you see what the nature of real problems are. You know, real problems tend to be much more complex than problems you can imagine in ways that you can't even think about. And that's when you really start to make progress.
Yeah, it's sort of an odds, like that idea of pilot and you saying that there are problems. It's kind of at odds with what we heard from, you know, the Teesside cluster, when they were saying the only problem that we've got, we don't have any technology problems. The only problem we've got is the pipeline and the economics. So, I mean, if we needed to deploy CCS, let's say we had all the money in the world and all the pipes in the world, and then we needed to deploy CCS on every cluster in the UK tomorrow, is that possible?
Yeah,
or is it still?
But what you do, and I think probably what will happen in most places, is that while you're doing a feed study, which will last a year or so, well, more than of the order of a year, you'll do a year's testing, and you know enough to go into the feed study and to get a design, but some of the final bits and pieces on that pilot unit that you need for the initial design will be verified by the pilot studies. And then probably you will carry on doing pilot studies, because you'll say, well, you know, this is how we'll build it, but we think we could save some money by doing this, that, and the other. And you'll probably carry on doing that as well. So part of the technical confidence comes from the knowledge that we can, you know, we know of workarounds for various things, and for things that we don't, we know how we can get an answer. And MHI working at DRAX is a very good example of them not knowing what they need to know, but knowing how they need to get an answer to what they need to know. If that makes sense.
John, maybe if I can add to that, I spotted in the list of today's webinar Chris Rayner. I do hope that is Chris Rayner from Leeds Uni and Sea Capture. And if I try to combine what you said earlier, then that would mean that, for example, Sea Capture, DRAX and Mitsubishi are going to talk about the specific challenges that they were probably seeing in the pilot plants.
Who knows? I mean,
you want me to say something, John? I am online, so I can say something.
Okay, Chris.
Here. I mean, obviously, what I can't speak on DRAX's behalf. Of course, they have a huge commercial decision that they have to make. You know, they're going to build a one absorber, or at least, you know, one system on one of their boilers, and then they will roll that out to 3 or 4 boilers, and they have to choose their technology that they're going to deploy on that. It's going to cost hundreds of millions of pounds, and so it's a very big business decision for them, and they need to know what the alternatives are available to them. So, you know, they have been doing trials with us, which is fine, you know, it's all going well, but whatever happens with us, they're still, because of just business due diligence, they have to look at alternatives as well. And so, you know, I certainly wouldn't read anything significant into it. They are doing what a sensible business would do, I think. And they you know, they want to do proper comparisons. And one of the issues they have, of course, is their flue gas is quite different to most coal or gas powered stations. So they need to understand the issues around operating on that particular site with things like amines or with things like our solvents or whatever. So, you know, it's a very interesting development. And so, you know, I think what it does show, if anything, is the commitment that Drax has to actually putting CCS on site, which is you know, really, really positive, I think. Yeah. I mean, with some of the other discussions, I've been listening very interestingly. I would perhaps add a couple of things on patents. If you ever tried to patent an amine, it's absolute nightmare. It is so, the patent literature is chock-a-block. And what you find is everybody's just trying to patent a tweaker or maybe a corrosion inhibitor or a degradation inhibitor or something like that, not the amine itself, because amines, you know, they were first patented about 90 years ago or something like that. So, you know, actually trying to get a patent on something that's an amine is actually very, very different. So very difficult. So it does mean that it's all these other things that you tend to be looking at. The other thing, the analogy with mobile phones is really interesting, but all I would say, John, is we still don't have total homogeneity on the charging sockets. You know, what you actually plug your mobile phone into to charge it up, you know, there's all sorts of chargers out there still. So not total homogenization on all of the process. So.
No, and I mean, I think when you get maturity, you will still have a range of technologies, partly because there's different requirements, and partly because, you know, that's just the way it is, and people want a few competing options. You know, the market wants some competition and some diversity. I think the real point I was making, which is, you know, was interesting for me, was just the nature of communication and the communication that's possible in the market. You know, despite people wanting to be as tight as they can, in some markets, you just have to, you know, information is available and things happen because that information is available. In other markets, it's not, or other types of products. So, you know, you will find, if people understand how the competition is better, then they'll try harder. So,
maybe one more question, if I may. So, Chris, why did you decide to patent C-Capture's technology and not keep it as the trade secret?
To protect ourselves, because you can't permanently, well, you can try and protect things as trade secrets, but, you know, things have a habit of getting out, and particularly, for example, if you're building a plant where you might be using thousands or tens of thousands of tons of a solvent, it's actually quite difficult to keep that as a trade secret, I would imagine, yeah. The other thing is, you know, investors, people working in the area, they value patents probably more than they value trade secrets. At least with a patent, you can actually go out there and protect it. And the other thing, I know we discussed a little bit about patents earlier, about the 20 years. After 20 years, you don't have to tell everybody everything, yeah? Once the patent's expired, all that means is other people can try and copy your technology, but you can't sue them if they do, yeah? But there's still, in many cases, a huge number of things to learn to actually be able to deploy a particular technology, not just because the patent's expired. You know, the patents only contain probably, I don't know, 20%, 30% of what you need to know to actually deploy a technology properly.
Thank you very much, Chris. Cheers.
yeah. Okay, anybody else got any? We've run over a long time. Anybody else got anything they want to say? Okay, I think we better stop there then. Karis, is there anything you want to add?
Thank you for speaking today, John. It's good to hear from you as well. I can give a quick, so next week we're hearing from South Wales and the Solent clusters, so the two clusters in the cluster series. And then for the Friday lecture, we've got Professor Lorraine Whitmarsh she's the director of the Centre for Climate Change and Social Transformations at the University of Cardiff, and she's going to be giving us a lecture on framing effects on public support for CCS based on a paper and some work that she's recently been doing, which we're really excited to hear from as well.
Okay, thanks very much.
Thank you for today. Thank you
for the
everyone
discussion,
for coming.
guys, and taking
everybody.
That's very interesting.
Bye-bye.
Thank you. Goodbye.
Have a good weekend.